Yeah, so the strings are immutable. But we have to be careful about what that means. We can't go to the string and change anything about the string. I can access individual characters from a string by indexing the string. You've all been doing this in the labs if you've been doing the caddis problems. Well, actually, you've been indexing the list, but people have been making mistakes in indexing the strings. But you can index individual characters and get the character out of it, but you can't change any of the characters in the string. Now you got to remember, when I have a string, there is a string that exists in the computer somewhere. And there is a variable that knows about that string. I can change like what's in the variable, but I can't go to the string and change anything about the string. It's immutable. And it is possible to, if you say to yourself, but I really want to change that string, my answer is tough, you can't. That's it. You can't. But what you could do is make a new string based on the old string, and when you make the new string, you make the change that you would want. So for example, here I have a string, is hello world, and then I say, okay, I want the first 5 characters. I guess that would be everything up like 0, 1, 2, 3, 4. I want to replace the comma with an exclamation point. So I am taking information from a string to build a new string. And then I'm storing that new string in another variable called b string. I could have stored the new string back into a string. It didn't matter. So I can't actually modify anything about that string. Now, this idea of immutability is going to be coming up a lot. And you might think, oh, okay, I guess that's kind of an annoying restriction, but this is actually a really good thing. Programmers love immutability, because usually that's a good sign that your program doesn't have side effects, or it can't have side effects that are going to sneak up and bite you. And it's easier to test, it's easier to wrap your head around. As soon as things become mutable, it gets hairy. It gets a lot harder to reason about your code, and that's when you're going to make mistakes. But that said, when it comes to our, let me call them like standard data structures, a list is one of them, they are all, by design, mutable. We can change what's in them, and that's kind of their point. But other than the data structures that we're going to play with, we like to keep things immutable. In fact, when we start to design our own types, which we do near the end of the semester, we are actually going to go out of our way to try to make these things immutable to help protect us from mistakes. This is a good thing. All right. Linear search. Linear search. I would say, if someone asked me, can you sum up, like, what's the most important core concept you're going to learn in 161? It's really hard to say, because you figure there's a lot you learn in 161. You start with Hello World, and by the end of the semester, we're making our own classes. And that's like what I was just talking about, making your own types and whatnot. So we learn a lot. At the end of 161, you will have nearly all of the requisite skills and tools in your tool belt to call yourself a programmer. Everything that you learn after 161 and 162. 162, we focus a lot more on data structures, which are very important. But after 161, 162, you're nearly there. After 161, you're nearly there. We learn a lot in 161. But if there's one big core concept that I think does a good job at summarizing, if you understand this, you had a great 161. And it is linear search. Assignment 1 was effectively a variation of a linear search. A lot of what we're going to do in assignment 2 is linear searches. Assignment 3 is linear searches. Assignment 4 is more linear searches. That's not to say a linear search is trivial, no, but it is a core, general purpose, remarkably important algorithm you're going to need to know. And you've already been doing it. And you've all been doing it, and when I say you've all been doing it, I don't just mean in 161. I mean, you've all done this in your life. Who here has ever had a stack of paper? Who here has ever had like a pile of tests given to you and you want to find yours? Put your hand up. How did you do it? You just go through the pages until you find yours, right? If it was sorted alphabetically, maybe you did a little differently. But maybe you just had a stack of papers. What do? Well, you look at the first one. Is it what I'm looking for? Yes or no? If it is, done. If not, keep going. Look at the next one. Is it what I'm looking for? If it is, good. If not, keep going. That's a linear search. You did a variation of this on assignment 1. Here's a Starbucks location. Is it in my box that I'm looking for? Yes or no? If it is, count it. If not, carry on. It's a variation of a linear search where basically you're going through some linear collection. When I say linear, I mean there's a beginning, there's an end. They might not be sorted, the order might not matter, but the point is there's a place where I can start and I can say, give me the next one. And you give me the next one. That's like the linear collection. And you're going over that linear collection and you're doing something with it. So linear search is a big deal, and you've already done it. So yeah, searching through some collection of elements to see if something exists with it is a very common problem, and its variations, of course. This is something you've done in real life many times. When writing algorithms to perform linear search, many new programmers rush through it and make some common mistakes. So here's an activity. Here's what I want you to do. Now, as a refresher, remember, we learned about loops, right? We learned about 2 types of loops. Wait, did we learn about the second loop yet? The for, yeah. So we have 2 types of loops under our belt. The while loop and the for loop, both of which will work perfectly fine for this activity. But here's the activity. Write a function called character is in. It takes 2 strings. It searches for a specific character, I'm calling it needle, within a string called haystack. If it exists, if needle exists within haystack, return true and false otherwise. When you finish writing your function, test it a couple of times. What do I have down here? An example of some tests? Yeah, so here's an example of some tests. So for example, all of these tests should pass. Remember, it goes needle, haystack. So, does the letter A exist in the string that is nothing? No, false. It's not there. Does nothing exist in the string hello? No. Does A exist in the string hello? No. Does H? Yes, it does. Does O? Yes, it does. So you write this function and then test it with those assert tests and see if you can get it working. I'm going to warn you. Take your time. Think about this. Raise your hand if you've ever done effectively a linear search in real life. Put your hand up. Everybody, I know you have. If you haven't, if your hand isn't up, you're a liar. Of course you have. So you all know how to do it. Just put it into code. But take your time, because I'm willing to bet a good chunk of you are going to make some common mistakes. Take your time. I'm going to give you a couple of minutes for this one because it's a good one. I've got a bit of a template here now. Maybe you needed a poke in the right direction of how to do it with a while loop. Now you could do it with a for loop. It's entirely fine. You might find that easier. Obviously, this is a non-working solution, so keep at it. Raise your hand if you're done. One person, two people, three people. Here, I changed it to a for loop template. Maybe that's more helpful to you. So raise your hand if you got it working to pass the test. Really high, I want to see. 1, 2 people. Raise your hand if you've got a working implementation, but it's not passing the tests. I'm surprised. One person?
A lot of us probably can't set stuff because Wi-Fi's not working right now.
Oh, is that right? Oh, well. Like, you could have said something 5 minutes ago. All right, well, I guess I'm one of the lucky ones with working Wi-Fi, but I mean, that's probably going to change in a moment. So, I feel like the internet in general, not just Wi-Fi, the internet's been really bad for like the last week, right? Yeah, I don't know what's up with that. Anyways. So, here's I'm going to do it with a for loop. So let me ask you this. First, I'm going to say, okay, for each character, I'm going to call it current character in haystack. It starts at the beginning. So if I have the string hello, what's the first letter I'm going to see? Then what? And then what? Exactly. So you understand orderedness of things. Good. So for each character, starting at the beginning, I'm calling it current character. If the current character is equal to needle, needle's the thing I'm looking for. If the current character equals needle, what do I do? Why? Yeah, it's almost a stupid question, right? Like, why? Well, because it's the thing I was looking for. If I found the thing, that means I found the thing. Right? So if that's the case, return true, right? What do I do if I don't find it? Continue to the next character, so I don't return false. You're absolutely right. Now this is one of the most common mistakes people will make. Is I look at the first character. Is it what I'm looking for? If it is, I'm done. Return true. If it's not, I didn't find it. Return false. But you only looked at the first character. We're not done yet. The moment I find what I'm looking for, I can conclude that the thing I'm looking for is in the collection. When can I finally conclude if the thing I'm looking for is not in the collection? Absolutely. If I look at everything and none of them were the thing I was looking for, if I ever get to the end and I never found it, only then can I conclude it's not there. And this might sound like, yeah, no shit. But this is such a common mistake. This would be, if you wrote it, if you did this, let me show you. If you thought this was correct, a bunch of these tests will pass. Well, I guess that one won't even pass. Because it doesn't return anything. There, it fails on the last one. And that was, I made these assertion tests in such a way where they'll all pass, but the last one if you made this mistake. This would be the equivalent, if you wrote this code, which if Wi-Fi was working, I'd bet at least a third of you would have done it this way by accident, which is fine. This is normal. This is a common mistake. But this code is absolutely incorrect for this problem. All it ever does is look at the first letter. This code would be the equivalent of me giving you a stack of papers and saying, find the paper on here, this stack of paper, it's not ordered in any way. Find the paper in here with your name on it. And you look at the first one, you go like, well, that's not me, therefore I must not be in there. Is that a valid statement though? No, that's stupid. That doesn't make any sense. You only looked at the first page. But that's what this code is saying. As soon as a function has a return, the function stops. Return ends the function immediately there. So if I'm looking at the current character and it's what I'm looking for, I'm done. If it's not what I'm looking for, I cannot conclude anything yet. I can only conclude that it's not there until I get to the end, meaning the solution is that. If I find what I'm looking for, go through the collection, One letter at a time. If I ever find what I'm looking for, great. But if that loop ever finishes, let's think about this. Let's reason about this code. One sec. If that loop ever finishes, that means we never ran line 4. Because line 4 would kill the function. It would stop running because it returns true. Immediately we're done. So if that code never ran line 4, that would be because that condition was never true, meaning it was never there. So if we ever finish that for loop, if that for loop ever completes, then we know we have looked at everything and never found it. Therefore, it couldn't have been there. What were you gonna ask?
Is that right? Or was that one just from the first one, the amount of numbers it is in?
I'm not sure what you're asking. This would run for each character, right? So let's look at the last one. The best thing to do here is what does the code say? I always like doing this. And you got to work with me on this. And I want to be clear. I know I said it before. I'm going to say it again. When I walk through the code line by line with you, I'm not doing that to be demeaning, being like, come on, class, let's go. I'm doing that because walking through the code and understanding what it's doing line by line is programming. I'm not doing it for any other reason than that's part of how I teach you programming. So I'm not like being obnoxious. You might find it obnoxious, but you're wrong. It's productive. So deal with it. So let's work through the last one. Actually, let's say I'm looking for, no, let's go through the last one. All right, needle is O. Haystack is hello. Obviously, we look at this, we know there's an O in there. But the code doesn't. It's stupid. So for each character, so current character in haystack, the first time through the loop, what is current character? Come on. I just made a deal with you that you had no choice in. You have to participate. Let's try this again. It's after a long weekend. You should be recharged and energized and ready to go, right? Or did you eat too much yesterday and you're still sleepy? Tough. Wake up. First time through the loop, what is current character? That was pathetic. I will sit down and we'll do this until I get people saying what it is. What is current character the first time through the loop? H. Hey, of course it is. Is H the same thing as O? Who said no? False. Thank you. False. So we skip that line of code. That's the end of the loop. We go back to the beginning of the loop. What is current character now? E. Everyone say E. Much better. Is E the same thing as O? False. So we go back. What's current character now? L. Is L O? No. All right. You said no. To be fair, I did too that time. So is L an O? False. All right. So we finish the loop. We do another round of the loop. What is current character? L still. It's again. Is L an O? No. All right, so we go back up. What is current character now? O. Is O equal to O? True. Therefore, return true. Awesome. That's what the code says. Now let's imagine we were doing the previous one, the A. I'm looking for an A. Obviously, up until this point, we haven't found an A. So let's pretend we've been looking for an A. So I ask, okay, is O equal to an A? False. Great, we go up to the loop, and then we realize we're out of letters. The loop is exhausted. It's done. There's no more that loop's going to run. So we jump down to line 6, and what do? Return false. There we go. Any questions about that? Now this is with a for loop. Now I'm going to show you something. If the internet was in here, some asshole would probably have done this. Aha, it wouldn't even work here. Nice. You did. Yeah, some asshole, right. So this failed on that one test, but let's get rid of that one test and see if it'll pass the other ones. Because that one test is kind of a funny one. So in, you can use in as an operator. Now in is an example of a keyword that is what we would call context sensitive, meaning how you use it depends on how it operates, just like addition. When you add two numbers together, its function is different than if you add two strings together. The context of how it's being used matters. Let me hit undo a couple of times. When in is in a for loop, like this, it's just the syntax for loop. But when you do it like this, in will actually tell you if needle is contained in that haystack. It'll actually do the search for you. Now, if on a test or an assignment I said write code to do a linear search, and you did this, I'd give you 0, because I'd be like, you didn't do a linear search. You just used, and in fact, I'm pretty sure in actually doesn't do a linear search. I'm pretty sure it turns it into a set. I'm not 100% sure, but it wouldn't have actually done a linear search, but that's neither here nor there right now. Point being, that could work, but it's not doing the linear search. Assuming in does do a linear search under the hood, you got to remember, if you're thinking, well, I could just call the function to do that, so why would I have to write that code? But you got to remember, that function you would call to do the work is going to do the work. That work still needs to get done. So that linear search still needs to happen, right? This will come back up later. So just as an FYI, yeah?
So why would that one return true for an empty string inside of hello?
That's a good question. I don't know. I haven't looked into it. My guess is every string. So here, you gotta work with me here, okay? How many H's are in the string hello? How many E's? How many L's? How many O's? Right? But how many nothings are there? Right? There could be, if I say, like when I look at that string, maybe there's a bajillion nothings in there. I wouldn't know because I can't see the nothings. So my guess, I want to be very clear, and the only reason I'm giving you this guess is because one person asked it and probably no one else in the room cares, but I'm going to answer you anyways because I think it's interesting, is my guess is what it does is it turns this into a dictionary of each character in there. How it does that exactly, like the method in which it does it, I'm not sure, but I'm pretty sure it probably turns it into the dictionary HELO and then like a nothing character, because there is always a nothing there. But it turns it into, did I say dictionary? I meant set. But the set is built on top of a dictionary. And then when you do the search, it's a lookup to see if something exists within that dictionary, which would be a constant time lookup as opposed to a linear search, which is a linear time look. So I'm sure that made perfect sense to everybody. But you know what, I could hit this point just a little bit. When I look at that, when we're talking about the linear search, I have 5 letters in the string hello. And I want to know if some arbitrary letter, I'm not telling you what letter it is, but I want to know if some letter exists in the string hello. Best case scenario, and everyone should be able to answer this. This is not a trick question. But understanding this question and understanding the answer to this question is closer to computer science than a lot of what we've done so far. It's thinking about the code. Best case scenario, how many things do I have to look at to know if that letter is in there? 1. Best case scenario is I was looking for an H. the thing at the beginning. What is the worst case scenario? How many things do I have to look at? All of them, all 5. So if the string I give you has 5 letters, you got to look at 5 things before you conclude something's not there. Because that's the worst case scenario, is the thing you're looking for isn't there. If I double the length of that string, how much more work do you need to do? Twice the amount of work. Does no one else in this room understand other than one person? If I gave you, let me put it this way. If I gave you a stack of 100 papers, and I asked you, check if one of these papers says hello on it. How many would you have to look at to guarantee that none of them do? How many? Give me a precise answer. There's 100 pages. How many? 100. If I doubled it and gave you 200, how many pieces of paper would you have to look at? 200. If I doubled the size, it doubled the amount of work you have to do. Makes sense, right? This isn't mind-blowing, but thinking about your problems like this is important. If I multiplied it by 10, how much more work do you need to do? 10 times. This is an example of what we call a linear time algorithm. The amount of time that your function needs to run grows linearly based on the size of the input. The input here being the stack of paper. If I double the amount of pages, it doubles the amount of work. It scales linearly, which is a fancy way of saying exactly what we were just saying. If I double the amount of work, it doubles the amount of work. If I multiply it by 10, it's 10 times the amount of work. You make the input bigger, I have to do more work. There are algorithms out there, where if you double the amount of work, it grows way worse than linear. Wait, did I say double the amount of work? Double the input size. Like even if I asked you to sort something, if I gave you, raise your hand if you've ever sorted anything ever. If I gave you a stack of papers and I said, sort these alphabetically, put your hands up. Of course you have, right? You've all sorted things before. Sorting, with the way you've sorted things, I'm willing to bet you've probably done some algorithm in your head that we'll learn about. You probably never really thought about the actual steps you did for sorting things, but you did do some algorithm to sort those things, like it or not. And I'm willing to bet one of the ones that you did would have been a quadratic time algorithm, meaning if I double the input, the amount of work that you have to do actually grows like to the power of 2. If I gave you 100 pieces of paper and I double it, you actually have to do like 4 times the amount of work. Which is weird, but you'll see and it'll make perfect sense when we get there. We're not quite there yet. But when it comes to your original question about how is in working, my guess is it's doing it with a set and it would have a constant time lookup, meaning now it would need to convert it to a set, which would be a linear time thing. But if it was a set already and it did the lookup, it would be a constant time lookup, meaning you could know if something existed in there in one step. If you doubled the size of the input, it would still only be one step. There's 1,000 asterisks attached to that, but it's very interesting. Trust me. We'll get there, though. Any questions about that little aside there? Raise your hand if you thought it was interesting. Everyone put your hand up. See? I knew it was interesting. Great. All right. So here's an example of, here I did it with a while loop, not a for loop. Here, count is 0, count. Here, I'm actually just going to go back here. I'm going to do the same thing with a while loop just for fun. if there, let's see if that's right. Cool. So here I did the exact same algorithm, but with a while loop. And I want to be clear, this is the same algorithm. The code is different, but the algorithm is the same. Start at the beginning, look at each thing. If I find it, good. If not, well, it's not there. So here I start with some character index at 0. So using the while loop, I'm going to index the string, where the for loop kind of did that work for me by taking each character one at a time. Start with the character index 0, start at the beginning. If the character index is less than the length of the haystack, go to the haystack at index 0. Is it what I'm looking for? Yeah, I'm done. If not, add 1 to the count. Add 1 to the index. I'm at index 1. Is haystack at index 1 what I'm looking for? Yes or no? Is haystack at index 2 what I'm looking for? Yes or no? And so on and so on and so on. So this is the same algorithm, but it's done with a while loop. Obviously, algorithm and code are very interconnected ideas, but they are separate. This is the same algorithm, just the code's different. But the actual steps, the idea of the steps is the same. Now here, this is the example of the broken one, right? Where like, oh, if I don't find it, return false. Well, no, I can only know if it's not there when I look at everything. So here is the idea. I want to make sure this idea is very clear because it's critically important. I'm getting really tongue-tied today. If, as I'm explaining this, you're like, yeah, I know, I get it, great, good for you. But there's probably people in here that are only kind of on board with what I'm saying, but let's reason through this to make sure I can convince you intuitively that this is correct. So we want to generalize this beyond strings. A string is a linear collection of characters, but we could have anything else, like a list of Starbucks locations. It could be whatever. I need a linear collection. We can confirm, we can know, and this goes back to the joke I was making before, but it's an important point to make. As soon as I find what I'm looking for, I can conclude that I found what I'm looking for. The moment I find it, I know it's there. Right? This shouldn't blow anyone's mind. This part so far is good. So let's say I've got some list, and I'm the algorithm. I might know how long that list is. I really don't care how long it is. And I don't know what's in that list. I just know there is a list, and its contents is a bunch of I don't know right now. When I start looking at because you got to remember, the computer doesn't know what's in the list. Your code needs to analyze, like your computer knows what's in the list and that like the information that's in the list is saved somewhere in the computer. But when I want to know if something is in that list, the computer can only look at one thing at a time. It doesn't know its entirety all at once. No, it does step by step, just like you do. So when I start, we don't know if any of the values in this sequence when we look at it. We don't. If I look at the beginning of the sequence and see that the value is x, I'm done. There's no need to keep going. So if I finally go and I actually look at the very beginning of that sequence and it's the thing I'm looking for, it's the needle, I'm done. Right? If I was looking for some other value like y, I cannot confirm just by looking at the thing at the beginning. I have no idea if y is still in that list. I don't know. It might be. All I know is that it's not the first thing, because the first thing is x. I would need to keep going. I can only finally conclude if something is not there if I have confirmed that none of the things are what I'm looking for. Which is a fancier way of saying, if I ever get to the end, and I never found what I was looking for, and there's no more things to look at, it must not have been there. As soon as I find the thing I'm looking for, I know that thing exists. But I can only conclude that it's not there after I've looked at everything. If I look at everything but the last one, can I conclude it's not there? No, there's no way. Because that last thing might be it. I don't know. Only until we've looked at everything. Then we know it's not there. And this is going to there. If I had a sequence of length 10, I would need to look at 10. If it was 20, I would need to look at 20. If it was n, I would need to look at n. Any questions about that? This is a very, very important algorithm. Now I can throw a variation of this algorithm at you really quick. Now this variation is actually really easy to do with a while loop. If instead of saying, I don't want to return true or false, no. I want it to return the index. If it exists, tell me where it is. So that's easy. If I find the thing I'm looking for at index char index, it's at char index. But here's the funny thing. What do I return if it's not there? This is an example of what programmers will call like a sentinel value. That is just a fancy way of saying, look, this is supposed to return an integer to tell me the index that it's there. But what do I return when it's not there? Well, we can return a value that here, -1 doesn't really make any sense. What index is this thing at? -1. Well, what? That doesn't really. So -1 has a special meaning that says that the programmer knows, well, it doesn't mean anything. And a lot of times, programmers will actually use constants. No. In a case like this, because again, it's a little bit more clear. If, let me go back. There. I change it back to the for loop one, but now if I say, okay, change it so this returns the index of the thing you're looking for, it's not so easy. I mean, there is an easy solution. You just add a counter. Obviously, these tests will fail because it's not returning a Boolean. But that should do the trick. I could just add a counter to keep track of the current index. But then suddenly I'm kind of losing kind of like the niceness of the for loop. So really, if I was asking you to tell me the index this is at, a for loop like this might not be as natural as a way to write it. The while loop may have been a little easier. All right, we'll end here.